Hi, this is Satya, and this is my implementation of the MLOPS pipeline for the heart disease risk prediction problem. So I built an app, and this is how it looks like. On the left side, you have like different views depending on the different personas. And this here is the architecture that I have built in the end. So there are mainly three flows to it, which I'll go over through in brief. So it all starts with the data here. So the data from UCI equivalence study is pre-processed, and we'll move on to the model pipeline where the models will be trained, and the best model would be packaged, and yeah, it'll be ready to expose. At the same time, we have the whole repo, the whole code sitting in GitHub, and CI/CD is enabled. So we have a code pipeline enabled via GitHub Actions. Whenever there is a new commit, the code pipeline would get executed, which has like a few steps. Tests would be executed, and if everything passes, then it'll be deployed to our application, which is running on the Kubernetes cluster. And in the cluster, you can see we have like about 5 different services running, including ones from the operations point of view, which we'll cover later. The main API application is exposed as a fast API, and the user who will be someone from a clinic, let's say, would have access to a UI application, which would be integrated to our Predict API, which can take patient details or patient metrics and predict whether they are having a disease or not disease. So let's move on to the next step, which is, or the beginning, I should say, which is the data preprocessing and EDA. So this is the view of a data scientist and what they ended up with in brief. So we started off with a data set of 303 rows, but then there were like 6 rows which had like blank values, and the fields were categorical fields. So we could not just simply impute those values because that will be adding facts without actually knowing the reality. So we dropped them. And in terms of the actual label, the raw dataset had severity from 0 to 4. So we sort of binarized them to bring it to disease and not disease. And we have like an almost even split. So we did not have to do any sort of sampling exercise. And if we go through the EDA part, we see that the ST depression and peak heart rate has the most correlation with the target. And also the subgroup heat map so shows that like asymptomatic chest pain, exercise anicnia together like gives about 87% prevalence, which tells us that the clinic where the clinical signal lives. And based on this information, we created 3 new features, which are rate pressure product, heart rate reserve, and all peak times log. And there's like a traceable line from here to the features of the winning model or the best model that we ended up with. So that's a view on the data side. So let's move on to the model or the ML engineer view. Okay, so now that we have the datasets ready, we go for the model experimentation. Our experimentation involved 3 main algorithms: the logistic regression, random forest, and XGBoost, and we trained them across the raw dataset as well as the clinical dataset, which is the one which had like the new features. And our main metric for finding the best model is the ROC AUC. This is because our dataset is almost evenly balanced, so that felt more like a better fit. We performed cross-validation, 5-fold cross-validation with the same seed so that it's reproducible. And you'll notice that like though the clinical dataset is what actually gave the best performance, it actually is not really helping out in the random forest side of the world. Just an interesting observation that was noticed. And also we have like a model card just to sort of depict a production case scenario, which will have the run ID, the feature set, the package versions used, the performance metrics, etc. Now the experiments are also tracked using MLflow. This is the dashboard for the heart disease risk exercise that we are doing, and you'll find all the experiments that we have done with the different models. And our best model is the logistic regression one with the clinical dataset, right? So if we go in, we get to see all the different matrices, the run details. So the whole point of using MLflow is that like we get to track the experiments so that if we do want to replicate them, we have all the variables required. It captures all the matrices nicely, and we do have the artifacts which will include the model packages, the serialized models, as well as artifacts such as the confusion metrics, the ROC curve, etc. So in a real case scenario, the experiment would run over all the permutation combination, like let's say if it's an AutoML, it would run over all the experimentations, and it based on the metric. In our case, that's the ROC AUC curve. The best model would be selected, and then it will be ready to deploy and serve. So now let's go over the application site, which is on GitHub. So this is the GitHub repo where everything lives. It's quite expansive. So we have sort of categorized or structurally defined like all the codes, tests, manifests, the decision logs, the different notebooks that we have used, screenshots captured for the report. The actual report itself would be inside the docs folder. And then we have a README which goes over how to actually set the whole repo up. And it's quite clean and nicely done. We have the Actions tab. So if you go to the Actions tab, so that's where we have set up the code pipeline. And with every commit, every push, this code pipeline would get executed, and only if it succeed will it be merged with the actual live service. So in all these cases, wherever you see green, it's all pushed and everything works fine. But then we have this one case where I intentionally created an error. So in this case, like the flow actually fails at the beginning itself. And then if we go inside, we get to see what actually went wrong. So from a debugging perspective, I'll just go back to the latest run just to show what all we are doing. So with every commit, we do a relinting, run 39 tests, a training smoke run, and we create a Docker job, which actually creates the container and tests the prediction. And if it all works, then the system will be deployed. So basically, if only all the tests pass, will the system would be deployed. And this sort of safeguards our application from any mistakes or errors. So with that, our best models are ready. Our application is all deployed and ready. So let's move on to the client side. So let's say the clinical view. So that's where we have the risk assessment. So just to mimic an application point of view, which a clinical firm would have. So let's try with a typical patient. So where you have normal readings. And what happens under the hood is that this app is linked to our Predict API, the model that is running on Kubernetes. And on call of the Predict API, we'll get a prediction as well as a confidence score against chance of disease or non-disease. So for a normal patient, here we are getting non-disease, and the actual chance of it being a disease is what, 33%, quite relatively low. Let's try with a high risk patient. I would just pre-populated some values just for the demo purpose. So we have like an asymptomatic chest pain, 3 vessels, low peak heart rate, and if we try it out, we'll see that the model predicts it as a disease risk case and with a high confidence score of 100%. Now, now it's generally possible that you can have outliers and maybe mistakes. So our application is sort of built for all those scenarios. So I'm just giving a unusually high value for resting blood pressure. And then rather than giving wrong readings, we directly say, okay, based on clinical studies or clinical dashboards or matrices, that's not really, it fails at the validation step itself. The idea is that we stay within the clinical guidelines. So that's the user point of view. Now let's take a look at an operations point of view, how things under the hood works, what a platform engineer who would be managing this application would see and would be maintaining. So this is the operations page. This is live from Kubernetes API. 2 replicas probe screen, the monitoring stack besides them. To mimic a real case scenario of serving multiple clinics, I have created a traffic generator that pings the Predict API with randomly picked real patient records, and that too at varying rate and with a few bad requests. So those are the invalid sends. Few bad requests mixed in just to showcase a real case scenario where things are not always perfect. Yeah, to show a glimpse of a production scenario. Let's see where all of this land. So this is the Grafana dashboard, which is actually keeping track of all the activity, and it's entirely provisioned with the manifest that's covered in the repository. Uh, so here you have the request rate, which sort of shows the activity. The latency shows that like if there is any issues in terms of performance, you'll find that the non-2xs or the 200x sort of responses, you have like a lot of fluctuations. This would be a flat or near flat, but since we are sending in invalid signals, this sort of captures that. So if you see any anomaly, we can capture it here. And then we have the prediction by risk, which shows, okay, how many non-disease cases are being predicted, how many disease cases are being predicted, and if there's any drift in the data set. These fields is where we can actually see the bump or the change or the anomaly. So Grafana gets this data from Prometheus, and yeah, it's linked to the two pods that are running. And Prometheus basically gets all the logs, gets the necessary data, and then passes it to Grafana, where we were actually seeing the metrics. And then we see that like it's both the services are up and running. And that's the entire pipeline that we have, from data to model to packaging. And then on the side, we have CI/CD, the deployment on Kubernetes, and how the user would be utilizing the said API, and the operation side of the world. Um, that's my submission. Thank you for watching.